So what I want to discuss here is to discuss. So I will strictly confine myself to quantum field theory. I will not write functional integrals and Wilson loops. Okay? I will not do that. Okay? I will be working strictly in terms of quantum field operators, Hilbert spaces, operate, and things of that kind. Okay? So the work I have done is relating to a new class of chemical potentials which we have found in QED as well as close. Okay. Here I should have added. So in a previous paper, we had casually noticed that there were certain terms which we can naturally add to the gauge transformations, which are already in the say in the canonical formulation. This is done with Parameshwaran, Sasha Pinzul Vaidya. They forgot to write this PDF was prepared only yesterday, and I forgot to write Andres Reyes Lega. It's a group of us who meet regularly, and we had written this fact in the paper. Okay? And after that, after subsequent months, especially after I came here, some new developments take place, and I'll tell you what it is. It appears to be it's a quantum field theory model. It seems to be have some good physical basis, but we can argue about it. Okay? And it has to be. It does have certain definite experimental predictions as well. So one can argue about it and maybe check experimentally. So to set the stage, I want to set the stage. I will work in 4 dimensions. Although it is, our older work is actually reviewed in a review article with Andres, and it is published. You can access it even by internet. So we have made a review of our understanding of gauge transformations, and I will work in 3+1 all the time. And I will choose a metric where most of the signatures is -1. So only time energy is +1. And what we mean by gauge group has to be understood carefully. It is the group of maps we are considering from your space-time into a compactly group, connected compactly group, like SU3 or U1. It need not be U. So it can be U1 in abelian group, but it's a compact group. So if I am working on a spatial slice, the element of this gauge group G is a function of space-time coordinates, which are called G of x at a given time. And as the magnitude of x goes to infinity, it approaches some element h of, let us say, the sphere at infinity. So we compactify, when you take the limits, we compactify by putting a sphere at infinity. This is the preferred compactification. And more generally, what happens is that you get a d theta space at infinity, and this is a section of the d theta space. So it is convenient to do this compactification. But if you insist on d theta space, I can also do that. It doesn't make any difference in the calculations. So this is the setting. And I may say that Arshad, and some of you may also be interested, was asking whether he can numerically simulate what I'm going to say. And he wants to do it in 1+1 gauge series, because it is very much more accessible for numerical work for a start. And he said he will start on it. it is not very difficult to formulate the basic ideas that underlie that. And it shows all the features I am telling you. Okay? So, the canonical coordinates at a given time, as we know, are the connections A mu and the electric field E mu. Okay? I should have put the index of mu upstairs, okay? Because they're conjugate variables and their commutations relationship is the standard one with I times delta cubed of x minus x prime. And I will also normalize generated to the algebra G with the normalization that the trace or any two of them is twice the delta alpha beta. This is standard. Whereas for SUN, in the n cross n, say, in the 3 by 3 representation for SU3 or n by n representation for SUN, and I can write the connection field as some n components, mu alpha in this basis, and I can write E mu in this basis as E mu alpha lambda alpha. So this is the thing. Now I start with the core arguments. It has been very long time ago. First issue is the following. What is a gauge transformation? Our whole activity is going to be centered around the Gauss law. It has very powerful consequences, and it is going to be centered on discussing the Gauss law. How do I normally write the Gauss law? We take the Gauss law, say, in any case theory, the starting point we write from in the, say, people doing the calculations from Lagrangians will consist of a Gauss law Q will be written as covariant divergence of the electric field, okay, plus the contribution of the matter field multiplied by, let us say, some smooth function chi. Normally people simply write the term and say it is zero on the vacuum. I don't want to do that because this by itself doesn't make much sense. It is a distribution. So you have to smear it with test functions. So I smear it with some test function chi and integrate it on d cubed x. Okay? I tell you the class of test functions which come here. So I Q, the generator of the Gauss law operators are Q of cascade. Cascade are these test functions. They are classical smooth functions on your spatial slide with some conditions at infinity, which I'll say now. Okay? So the brackets here indicate a trace over Lie algebra indices, okay? And Di is the covariant derivative. In the U1 case, there is no need for taking the trace, and the Di becomes the ordinary derivative Di, small Di, because the electric field is neutral. Okay. Now, here cascade is a Lie algebra test function. Okay? In the non-abelian case, we can write it as a point x of space-time as chi alpha of that point, that is lambda alpha, where the functions chi alpha approach these functions chi alpha approach functions of x at infinity. So normally, so that is I don't say that the chi goes to zero at infinity. I don't want to say that. That is not a priori given. So this equation as written is not very precise. So I want to make it more acceptable by doing a partial integration first. So I write the Gauss law in this form. Okay? So it's a test function chi indicated multiplying minus covariant derivative of E plus J0. And in case the components of chi go to zero at infinity sufficiently fast, I can do partial integration and I get back the Gauss law and they will all vanish on the quantum states. Okay? Because of the equations of motion, they will vanish on the quantum states. But that is not compulsory. Suppose chi does not vanish at infinity, then this does not become the Gauss law. Okay? It is something else. What is it? When chi does not vanish at infinity, chi cascade need not vanish on the quantum states. There is nothing it says that Q cascade vanishes on the quantum states if chi does not vanish at infinity. Okay? And they generate a group, okay? And that has been called long ago by Mysore and Sachin in a paper as the sky group. So we call it as the sky group because in this action on the quantum states, what is relevant is the value of chi at infinity, because all terms in chi it vanishes locally, vanishes on the quantum states. So the quantum state coordinates out these terms, and you get only things at infinity. So this is something that is living at infinity. So we call it as the sky group in our paper, and our central attention will be on the sky group. And notice that the sky Q cascade also generates gauge transformations, but the gauge transformations it generates have test functions which do not vanish at infinity. Oh, so one point to notice is that this, even though Q cascade is not a Gauss law generator, when chi doesn't vanish at infinity, because of locality, because of the fact that these observables are involved in a generator from local fields. They are all their they are creating test functions locally. The effect of commutator Q chi on observable only depend on the local behavior of chi. So this Q chi, even though it may not vanish as an operator like a Gauss law, nevertheless they commute with all the local observables. So this object here commutes with all local observables and performs gauge transformations, but they are not the standard gauge transformations because the gauge functions do not vanish at infinity. And this fact has been written by us for a long time, I should say. Again, very long time, ever since Kumar Gupta was in Syracuse, okay, maybe Govindarajan also was in Syracuse. We wrote it first in the Chern-Simons case, then it was several papers along these lines, Elisa Ercolisi, many people, so many papers on this followed. Okay. Now I shall now argue that these terms have very strong consequences in physics. So that is what I want to talk about today. Consequences not in the mathematical sense of proving theorems. Okay. It appears to have direct physical consequences which maybe can be tested. Maybe can be tested. Well, they're correct, I do not know. Because connecting a formulation with experiment is some intervening assumptions, which I will tell you as I go along. Okay. So, I want to talk about novel chemical potentials now. Okay. Now, what I will do now is to take this standard Hamiltonian H0, which is, as you know, consists of for QED and QCD, E squared plus B squared over some constant for the for the gauge theory part plus the J0 term integrated, and that is your H0. It can be interacting. In fact, it will be interacting if it is non-abelian gauge theory because there are cubic and quartic terms in the Hamiltonian. Plus, what I will do is to add another term and add it, I call it H1, and then add it to H0. What is this H1? This H1 I will add is this Q of chi, this generator of gauge transformations, possibly large, with a constant in front, and the constant has the dimension of energy because Q chi has no dimension. So a dimensional parameter fits in here. Can I do this? Well, I will give a physical interpretation of what this is. I will show you that in the standard chemical potential people write in QED is a special case of this. And I will also show you that this does not change equations of motion. Adding this will not change equations of motion, but it will change in dynamics. Okay?
Does it assume that there is some density of particles which is not zero?
Yes. So so I will tell you. Yes, those are all classical statements. I have no I have no comments on classical statements. I don't understand it well enough, but I will show you that my interpretation will be that it is the experimental preparation of the situation. So it's a coupling of your system. So constant density means some experiment is happening. I suppose it means
something like a flask.
So something experimentally is getting prepared. So I will see to make an argument that this Q cascade is coming from the experimental setup which is observing the system. Okay. That is the interpretation I will give. Okay. I will give supporting evidence. I think this will contradict what is said about the standard chemical potential. But for now, the standard chemical potential is a special case of this, as I show you now.
Are there any other examples of this kind?
Any kind, you can choose any kind.
No. What I institute Lagrange that don't have tie there, right?
I'll show you that it is there. I'll show you in 1 minute. Next slide. Okay? I'll show it to you. Okay? It is already there. You drop it. Okay? Normally it is ignored, but it is there. I'll show you.
So you can integrate this over a large volume where the rest of the terms are bound to zero. But you
I don't again. Terms going to operator going to zero in my context has no meaning.
So it's
Then I don't know what is the meaning of distribution going to zero. Because these are distributions in R3.
test function. Or integrated test function.
If you then you are changing the theory, I am dealing with the theory on R3. So I am allowed with all test functions, and what happens to those test functions depends on the quantum state. So what happens in infinity is controlled by the quantum state, with respect to which you take expectation values and get numbers.
So my question is, how do I operationally set up such an experiment?
I will try to come to that later. If I have some speculations. I would say that they are still speculations, but I'll come to that later. Okay? I am also worried about it, and I would say that it is largely an open question. But the idea that I am telling here is not, in that respect, not new. In fact, it goes back to Niels Bohr. Okay? Then it comes back, just come back again and again in different avatars. Okay? I should give the things. I don't know the answer fully.
Suppose I find the vacuum expectation value of H. Will it be zero or not?
It will not be zero, the energy will be shifted. If there is a cube cascade of an appropriate kind. Okay? So the scale of this term is determined by mu. Okay? So that is the question you were asking, but it comes in this formulation, and let me see what happens. Okay? Then we can come back to open questions. There are many open questions, we can come back to open questions. Okay? But the first term I want to say is that if you use this Hamiltonian, it will not affect equations of motion. Not at all. Why? Local operators, Q-chi only performs local operators gauge transformations locally. But the equations of motion are gauge invariant. Okay? So when you write the equations of motion for the quantum fields using this standard equations of Hamilton, nothing will change. A local equation will not change. Okay. So, effect of this term will not be felt in local equations at all. So, it will not be felt classically at all. Okay. So, what I am going to tell is strictly a quantum phenomenon. So, as I said here, later I will interpret it as a coupling of the experimental setup in the system. Yeah, but if it is correct, it's a model, maybe wrong. It will also provide us with a model for how experimentally we extract information from nature. Okay? This is still an open problem, but I have said many times here that you need the emergence of a commutative algebra at infinity, and we will see that this happens in this model. Okay? So, is this commutative algebra appropriate for extracting the information? So, I have to give you more details on how the experiment is set up and so on. I don't know the answer to those things, but I have an answer to the emergence of commutative algebras. So, as I say, this is an ongoing work, and we have to think maybe it's wrong. I don't know. That we have to maybe wrong, but it is certainly better than what has been done till now. On, in my opinion, confinement, where you do one thing and you do another thing.
This chemical is right?
Here also it is the same. Because Q-chi, still here, this Q chi is commutes with H0. Okay. H0 is a standard Hamiltonian and Q chi is a generator of large gauge transformations.
So what kind of charge?
This is non-abelian, it will become a non-abelian charge. So that is the novelty of my statement. Okay. Otherwise, I will be saying something everybody says.
So for you want the regular charge. For you want the electric charge.
For U1, you choose a constant Q cascade, you get exactly the number of operator times the mu. J0 times, just the standard result, because the electric part in Q chi will disappear and you are left with J0.
So
You are left with J0 and that is the electric charge. Okay, so this is a generalization of that term. Okay.
So you need the non-zero expectation value the number of it for that to solve.
No, again that depends on the state. Okay. I emphasize states and operators are different.
I look for vacuum.
In the vacuum state it is zero. Obviously, even in QED, if you take vacuum state, number of operators is zero. So whatever operator you are talking about, in the ideology I am proposing, has to extract numbers only by coupling it to a state. Otherwise, it has no meaning. It is an operator in some infinite dimensional Hilbert space. That's it. But if you have to extract numbers, you have to couple it to some state and take expectation values. So it depends on the state. So what I am going to do is see this interplay between states and operators and how things can change very much.
Because the metal sector was completely absent.
That is, you can do that.
The charge here,
In the abelian case, you will get zero charge. The non-abelian case, no.
pure non-abelian.
You will get answers. It will not be zero because the first term will not be zero.
Identify it.
It will be glucose. It will be some colored states of the.
Glucose don't have charge.
And there is a SU3 acting on that. Okay. So there is a SU3 symmetry for QCD, even purely angles, and there will be there is a representation of SU3. Since formally you can write out this Q cascade, this term is not there, J0 is not there, will generate for cascade going to some Lie algebra element at infinity, will generate SU3.
Can we say that glucose number is conserved in the, for example?
If I know what is a blue ball, which I don't know, okay, so you have to give me a quantum state describing a blue ball, then the quantum numbers of the blue ball up to a complete commuting set will be considered. Notice also some new feature comes. Sachin and I already observed long ago that this is a non-abelian group. Is commuting with Hamiltonian. It is not abelian. So in a quantum state, Dirac has already taught us in 1928 or 29. He knows the years that we can only diagonalize a complete commuting set. That's the only thing you can do. Okay? The rest will change it. So if the complete commuting set of the blue ball can be diagonalized.
Glucose are basically lots of.
I don't know that. It's a classical.
But they are both.
I don't know what that means. Quantum mechanically, I don't know what that means. It's not a classical system. As I say, I don't want to talk classical physics where things are happening in space-time. I don't know how to do that. I can change my face and start talking about classical physics. But that I think is doing mutual funds. You take a little bit from here, a little bit from there, put it all together and make money. I don't want to do that. We need a coherent picture of the whole thing. So whatever I do will be quantum. Maybe that, so anyone who says there is a blue ball, it is some ball, and I don't know what that is. You give me a quantum state.
So you need the base there, but not put Q alpha and Y alpha.
You can do that. You can write, it's a linear, so you can write. You can write as Q alpha lambda alpha. Q alpha lambda alpha.
In that sense, I mean, you don't have gluons.
I don't know what that means.
We can find.
I don't know what that means. I will diagonalize these operators in a minute. I don't know what that is. But certainly you can write Q of chi as Q of chi alpha times. So Q alpha You can choose here, okay,
Right.
the chi alpha and take lambda alpha here, and the trace of lambda alpha with this you can call Q alpha. So then the left hand side will be a linear combination of Q alpha. That you can do certainly. And let me proceed. Okay. Let me not bring blue balls and font confinement and so on. Okay. Let me say I don't know anything about it. Okay. Because I don't want to get into debate on whether they make sense or no. So let me say I'm ignorant of those things. So we have found this result already, I think with Kumar Gupta for Church and newspaper. Okay? And there was this review with Andres shows how this arithmetic behavior is very important. In the Church and case, we found the Kathmandu algebra, I think long before anybody else found, including Mitchell and Leiberg and Mitchell. But anyway, that's a decades old story. Okay. So this is again a repetition. The exponentials of Q will generate for different test functions will generate a group. But it's an operator. So there's an algebra I can generate, and that group that I'm generating is what we call as a sky group. But notice that in my case, the skies are algebra valued functions, okay, at infinity, not constants at infinity. And furthermore, in the non-abelian case, they are non-commutative. Okay. In the abelian case, they commute, but in the non-abelian case, chi of q of chi1, q of chi2 commutative. So here is what, so Dirac process, okay. A is my algebra observables. These are the color neutral objects because, and they are local. Locality is important. Okay. You don't take Windsor line going away to infinity. That will not be local. That is not gauge invariant if it runs to infinity. Local operators. In fact, Windsor line will come back in a minute. Then, the irreducible representation A, the algebra of observables, is characterized by a vector state diagonal in a complete commuting set. If you want to examine the color sector, it will be characterized by the eigenvalues of this of a complete commuting set of this algebra. That otherwise I cannot diagonalize them simultaneously. So only a complete commuting set can be diagonalized simultaneously. So every irreducible representation will be characterized by a complete commuting set. So in the case of SU3, yeah, so this is my state I am telling about. What is, I'll tell you how to write this state, but once I write the vector state, I have to ask whether it is stable under time evolution. But now the time evolution, however, has chemical potentials of this kind, and they are not chosen necessarily from the complete commuting set. They can be you choose your special kind, it comes from some other consideration. May not commute with the diagonalized operators here. So what will happen? After time evolution, you will change the vector state, the operators in the diagonal operators in the complete computer set by unitary conjugations. So you will change the vector state and it will cut. And what you have diagonalized initially will no longer be stable, it will go on evolving. And we will study the evolution, and I will argue that because of this possible evolution, generically, mean values of color observables will be 0. Okay? And that is my proposal for color control. Okay. If in case this extra chemical potential does commute with the operators they are going to diagonalize, then I will call it as a color confined state, color deconfined state, because now you can see color. Okay? But the ones which you start moving around, you cannot measure the color because it keeps moving around. So if you try to look at the average value of color, you get 0 because the time scales are 10 to the power minus 23 seconds of strong interactions. And I have even asked people doing calculations in LSC whether they can see the time scale, and they said no, they are only looking at averages. But the model I am proposing will give the averages to be 0. So You can't see color. Is that confinement? I don't know what this space confinement, what it means. I'll come to that in a minute. Okay?
How do you get this sense?
Hmm.
Where is the time scale coming or entering?
10 to the power minus 23 seconds is the time scale coming from x0. The full Hamiltonian is x0 plus h. Okay? X0 is the strongest ranking Hamiltonian. That is the time scale. Whatever it is, from what I know, it is 10 to the power minus, about 10 to the power minus 23 seconds. Okay? About that. Okay? So, unless the experiment can probe inside that, which I am told you cannot be done, it makes no sense. You will get some kind of an average. I will show you in a minute that the average will be generally zero. That's what I will show. Whether you want to call it confinement or not, I am not prejudiced. You can say this is not confinement, okay, but you cannot see color. To see color, there is another phase where the chemical potential commutes with what I have diagonalized. That will not change the state, and their color will not change. That's fine. You can see color there. So you will see immediately there are two phases in this picture. Okay. So here I want to answer by somebody's question whether this term is there in the canonical formulation. Who asked this? You asked it. It is there because if you look at the Lagrangian and you do the Legendre transformation, you get this term from Fi0 term in the Lagrangian. You get this term, which is the Fi0 is the capital Di A0 times Fi0 is the electric field. So you get this term automatically, where this A0 has no conjugate momentum. It is the theory there is no conjugate momentum K0. Okay. So what people normally do is to assume that A0 goes into it's a classical field because there is Phi0 is 0. That's what they say. It's a classical field. There is no conjugate momentum. They say go to 0, I do partial integration, this Gauss law, they drop it. They drop this whole term. But that is not allowed because we don't know how A0 can behave as infinity. I am telling you that we told in our papers that if you take A0 not to vanish it is some there is nothing which will move. There is no conjugate momentum to A0 at all in the theory. The Phi0 is identically 0 in the theory. There is no conjugate momentum. So this is essentially a classical function, and I can choose it to be whatever I like. And if I choose it to be my cat cake, which is what I am doing, you get a case where A0 does not vanish in infinity, and you will generate the terms I am talking about. And this term is already there. If you do Lagrange transformation from the Lagrangian, this term is already there in the Hamiltonian. What I have added is not new, it's already there. So this is the point I want to make. So in some sense, what I am saying is not revolutionary, it's just there. J0 term also, so what you do is, what if you can do partial integration here? It's simply a Gauss law. So people simply throw it away. And then you have this problem of gate fixing and all kinds of things. But I am suggesting that, or I should be careful, in the paper with this group here, we had already noticed this fact and argued that maybe this term is not 0. Okay? But perhaps we did not go far enough. Okay? So why am I interested in this term? Okay? The first thing you notice is that this term, okay, I am adding this term okay, to the form momentum of the theory. So the form momentum of the theory now has become the standard Lorentz invariant form momentum plus this term, okay, where this is a delta mu0 term there. This form momentum is certainly translation invariant, no problem, okay, because there is a d cubed x integration. The different components of this t commute because this term commutes with t. These are gauge invariant for local and all gauge transformations. You can see from the formula for B, no problem. But it is not Lorentz invariant. This will not transform as a 4 vector because of this extra term. So the Lagrangian I am writing has the property, the Hamiltonian I am writing has the property that it will automatically break Lorentz invariance. Is that a troublesome fact? I claim no, because there is now a bunch of papers. I should say several dozens of papers which have proved in various ways that QCD and QED and QCD break fluorescent barriers. This is known. I don't think it is a new result at all. It is known, but somehow it is not diffused in the community. But fluorescent barrier is broken. People say that he especially keeps asking me what is the scale of this breaking, and it's coming from the infrared cloud. So there was no way to control the scale at that level. But now, at least at some level, one can control it because it is given by this mu. It is coming in the chemical condition. So there's a scale. What is the meaning of this scale? I'll come. Okay. I think it is really a setup for the experiments. So I'll come to that in a minute. But more interestingly, yeah, I have given some references. Yeah, this is more interesting. What is the dynamics? So, as I say, to my mind, we should go away. We should train ourselves not to think in terms of classical physics. And if you want to try to understand what's happening in quantum field theory or at the microscope level, you should not start thinking of space-time and group balls and so on. I don't think that is how, at the fundamental level, nature is. We have to understand how these things are happening from a fundamental level. So, maybe this is not a correct way to approach it. Quantum field theory is not a correct way to approach it. I have no problem with that. Okay. But anyway, it cannot be writing Lagrangian and dual function. That I am sure. I think those days are past. Again, it's my personal temporary opinion. And as Govindarajan will appreciate, what is it?
Changes.
What is it? Abhiprayam can change entirely. So after a time I may change. But for now, this is what I believe. Not believe, I think. Not a belief. Somebody challenges me, I don't mind being wrong. This is not earth shaking. Okay? So this is what I think. Okay? So let me see what happens. Okay. So this the main point I want to show you is that this Q cascade which I am diagonalizing, the complete community set I am diagonalizing, commute with all local operators. Okay? So the way I am diagonalizing, these diagonal operators are labeling the super selection sectors of the theory. Okay? Because not only can change it. It's like other operators of angular momentum. No, nothing can change. So the different representations of angular momentum with different Casimir operators are different super selection sectors for the angular momentum algebra. Because nothing can change the Casimir. Here the corresponding things are these complete community sets which you are diagonalized. Okay. Okay. And the complete community set is necessarily a abelian algebra because we cannot diagonalize non-abelian algebras and find simultaneously. Okay. So we are normally following Dirac, we will diagonalize the maximal abelian subalgebra. Okay. And for SU3, okay. For SU, for QED, it will be the charge operator. Okay. So we diagonalize the charge operator, and that is the one. So the charge will be 0 vacuum sector, or it may be 1 electron, Q is 1, and so forth. Okay. So in the QED case, this Q cascade. So this cascade is Q. Now standard you simply integrate J0. But in my case, you are not just integrating J0. Here, this for QED this term is not there. But J0, after just choosing A0 to be a constant, equal to the density of the charge as well as existing, I am allowing it to be a function of x or the coordinate. Okay. So in QED, choosing different A0s with different dependencies at infinity, constant will give you one chemical potential. It may be at infinity, which is in this case, it's a two here at infinity. You can take different YLM functions for A0, expand, you will get infinite number of chemical potentials for QED. So if you want to make a phase plot against of temperature versus chemical potentials, it will not be a two-dimensional plot now. In this model, it will be an infinite dimensional plot, but you can start with say temperature versus H0 equal to constant. The second moment, then you may choose angular momentum 1 for H0, angular momentum 1 and 2 for H0, whatever. Each of them will give a different phase plot, and each of them, hopefully, one expects will give different possible phases for QED I am talking about. So already in QED, there is a very rich structure that is emerging. Okay. Now in QCD, let me do the calculation now. And here I will tell you. So what are the things I can simultaneously diagonalize in QCD?
J0 which you have actually matter charges.
Hmm.
In principle, we should study the theory with matter and electron as an interacting theory, not separately like
No.
bypass the. And you are not doing that.
No, I am doing that. What?
You are not doing this kind of quantum theory for J0.
No, exactly. Understood. No. The charge density. No. See, I have not given you a combination relation. So why? How is J0 written in terms of matrices? So in QED, it will be side-dagger side. Side-dagger comes to charge. So it will be side-dagger side. Right? In QCD, it will be side-dagger lambda alpha side. Okay, I allow you, but I will not need the detailed properties of the matter set. So I am not trying to solve the H0. The standard calculations of H0 being asymptotically free and so forth, which are perturbative results, I am not bothering. They are all there. I am not doing anything to them. I am only concerned with what happens in infinity. Okay. So you are right, but so far as I can tell, I am not disturbing those results at all. The standard results of QCD, I am not disturbing. I am going to disturb what happens to supersolution structures. And whether the QCD charges, QCD as a group, can be implemented as unitary operators on a Hilbert space. That's something involving infinity. None of these gauge transformations are localized. They are looking at operators because you are writing operators with test functions that are non-vanishing, and you're quotienting that thing by all operators vanishing which vanish at infinity. So it's equivalent class of operators which can be thought of as living at infinity, and that's what gives you the QCD or QED charges.
Problem is this topic will be I don't have any control on of the universe. I have probably control on probably a large lab-like structure in which my experiments will be done. So you have to talk within whatever is that finite domain, what happens.
Yeah. So
is there an operational procedure which I can to do that?
Yeah. So this you have to tell me the scale of the system that you're dealing with in QCD, how I fix this. So I have to tell I have to know what is the scale in which this QCD experiments, the interactions take place in QCD. I have checked the time scale, which is of the order of 10 to the power of minus 23 seconds. And the length scale in which the interactions go away in QCD, offhand, I don't know. It is
say that therefore minus 23 velocity.
No, it will not be like that because it also affects atomic physics. So it 10 to the power minus 8 centimeters. So it will be the order of maybe 10 to the power minus 6 centimeters or something like that. Here I don't know.
Physics itself is about
13.
15 meters.
30 centimeters. Yeah.
That is the kind of scale which we have. Now the lab experiments which I'm doing are on the size of say meter and other things. For that, many of these remarks, the scale which you are talking about is too large compared to the scales. So if it goes like 1 over L or 1 over
What is going 1 over L?
whatever corrections you are looking for.
This I don't know because your question is well taken, but I don't know that this start die away after distance. I don't know that. because these are QCD charges. So we know electric charges, even if it's localized here, I can find the electric charge by measuring the electric field at a very large sphere. Don't go away. Okay. Very large sphere. Maybe you may put the charge here, take a huge Gaussian surface, it will be still there.
No, operationally, it is not fundamental. That's what I'm saying.
No, because it is measuring fluxes at infinity. For QED, I don't know very scale. QED, because I am interested in saying, for example, I have a localized system, how much charge is there? I can find out the charge by measuring the electric field at very large distance. Okay. It doesn't die away at all.
So, principle, that is, in my way of looking at it, in the case of if I say the photon has a very, very tiny mass, 10 power minus,
I don't know.
no, 10 power minus 22 electrons. Then even if you do the difference, if you go like e power minus mr by r or various other, that term which you are multiplying is almost 1.
I
You will not find any difference in all these.
Okay.
That's all even I'm showing you. They get the vast limit for photon only by that kind of an argument.
Okay.
So I don't know whether operational will make any difference.
I don't know the meaning of operational.
Experiment.
Experiment. So I will only talk about experimental things. You know the right. I have maybe that the effects I am talking about.
It's true that if there is a large amount of charge, the charge which is there is very, very large, then that can make a difference.
So I don't want to. I don't want to commit myself. Really, right? I don't know. Maybe this whole thing cannot be seen. I don't know. But let me go on within my knowledge. I don't know within the logic of what I am doing. I want to be firm finally. Maybe it cannot be seen. I don't know. Let's remember that when quantum mechanics came, many of the things they said were a mess. They did not know what they were doing. They were trying harder and harder. Bohr wrote such complicated papers trying to understand what it is they are doing. So it is like this. If they may be wrong, no problem. But I want to say something, maybe it is normal. So I want to diagonalize so some completely commuting operators from SU3, and what are they? Well, it's a group algebra. So certainly the Cartesian operators of SU3, C2 and C3, two of them, can be diagonalized. And they commuted, they have the property that they will commute with all color transformations. I can diagonalize. Then normally what we do in the SU3 case, say the 3x3 representation, for example, is a rank 2 group. So we take third component of iso spin, okay, and a hypercharge after you select a preferred U2 group from SU3. Okay. So these are coming from some preferred U2 group in SU3, and we pick I3 and Y. This is a standard notation in SU3. So the states are labeled by eigenvalues of I3 and Y. And there may be other things coming from H0, which I am not talking about. Okay. So the Q cascade tilde, the tilde denotes the operators of diagonalizing, are coming from test functions which are becoming functions of x hat at infinity. So they are not constant anymore for me. Okay. Now I do the following. I diagonalize them, and I choose a chemical potential, which I call H1, with a cascade which does not commute with cascade tilde. Okay. So what happens? So that is what I was. So if I choose a generic chemical potential, it will not commute with cascade tilde. So this is not. So the term in a Hamiltonian H1 term, it will commute with H0, no problem. It will not change the equations of motion, no problem. But it will change the quantum state. So it is in this cascade tilde. So as time evolves, the diagonal operators will start undergoing conjugations as you keep going. I'll do the calculations. And to choose a new cascade, which is a cascade appropriately, all this you are finding in cascade tilde is actually a dense orbit. It goes on and on and on and never closes. Okay. in the space of the Lie algebra, it never calculation, it never goes on and on and on. It never repeats. Okay. So if you take an average of any color observable in such rotating state, you get zero. No chance of getting anything else except zero. Hmm?
The area within curve or
Yeah, but the point is this. But the point is, you start from a particular Kaplan subalgebra, you start from a point in Q cascade, but it never returns to that. Yeah.
it's the area within curve.
It doesn't feel, I don't know which area, that's what I'm saying. You start from one Kaplan subalgebra, goes out to another Kaplan subalgebra, a third one, then I prove that it never comes back to the original one. Okay. So it goes on. Why? Because it is another theorem that the only automorphisms of the Kaplan subalgebra are the wide automorphisms. Okay. This is known. The wide automorphisms, presu 3 is S3. So each element has a period 6. So the orbit, if it closes, should have period 6. But I checked whether my operator has period 6. No. It has no period. You go on, you can multiply. Go on doing this and upgrade. It will never close, it goes on and on. So, what is the area it is filling? You see, so it is going like this, and the sutra is compact, it is accumulating somewhere. What is the closure of this cell? I don't know. This is one of the things which I want to discuss. I want to understand, but I don't know. So I want to show you how. So, but I can also choose the cascade, which doesn't move cascade till there. For example, I can choose cascade also to be cascade till there, the diagonalized operators. Then nothing will change. The state I have chosen is stay there. In that case, there is no problem in seeing color in this model. You can diagonalize color operator. You can see expectation values of color. No problem. So I will call this as color deconfined cases. There are definitely these two possibilities. So let me do a calculation. Okay. Yeah. So
probably measure zero. That kind of.
Yeah, I'll come to the very good question. I'll come to that. This is a problem in dynamical systems. Okay. I have checked. The problem is that dynamic systems in system algebra, what happened to attractors and so on, I am unable to find the literature. Okay. I'll tell you why, and then I'll stop because time is getting. So people talk about color confined and deconfined phases. Okay. Let me tell, I have no idea what this means. Because the only understanding I have, which is satisfying to me, will be that the color confined phases are not in the domain of the Hamiltonian. So I have to write everything in terms of operator theory. That's the only meaning I have of color confined phases. That the Hamiltonian is a huge thing. There are many lectures which are not in the domain of the Hamiltonian. Govindarajan actually knows many examples. I think what this means should mean he said it is not in the domain of the Hamiltonian. I do not know if Wilson line calculations accomplish anything like this. I don't know. Okay? Could be that there are two theories going on here. One is this, the other is Wilson line, and the twain shall never meet. That's fine. Okay? One may be right, the other may be wrong. I doubt it. I heard Ravindran the other day, and he was talking about quarks all the time. So for him, quarks, actual quarks is very important. So are there several things happening? This is exactly what Arnold told about Genfund, like doing mutual funds. Take something from here, something from there, put all together and make money. And it looks like that to me. Maybe I'm wrong. Somebody can deconfine, but convince me otherwise.
So, I'm fine, but too easy. That's right. Other cases will not happen. But they ask all these questions and you want also. Now, when you say that there is apartment in that case,
there are actual proofs. Actual proofs. Like I think it is. There is no Sweka, I think. There are actual proofs. And also maybe in this new paper of Mundekar, 2 plus so and 1 plus 2 plus 1, I think, is Schunger model. that the spectrum of the Hamiltonian has, because there is no charge in the spectrum of the Hamiltonian. This is proof. Okay. That's the kind of proof I am looking. Okay. You show me prove that the spectrum of the Hamiltonian has no colored state. Okay. I don't have any such proof. Okay. Yes, Wilson line proof, I have no idea. Because if they don't show me what is the Hamiltonian. If I ask the question, what is it? They abuse me. I don't want. Either abuse. Okay. If you are not satisfied with it, I have nothing to say. If I am not. I find that I'm. What is it? Many winds are blowing on me and they are not necessarily in the same direction. I think so. So, I just want to show you. So I want to show you that the orbit of the states can be avoided. Then I'll stop. Okay? Then if there are people, I think Gurudhajan is giving a talk now, right? There is plenty of time now.
So students,
Students, there's a class.
from IITs,
Okay, fine.
B5.
Okay, so let me just show this. So let me show how the ergodicity can happen. It's, I think, quite interesting. So I diagonalize I3 and 1. Then I diagonalize them. There's cascade I choose. The cascade till there. I diagonalize. Third component isospin and hypercharge. This is a three-dimensional representation. And I3 and Y eigenvalues. So it's on the vector is a three-dimensional vector. So A, B, C as a column. In the I3 and Y are diagonal operating, 1 minus 1, 0, 0 for I3. The other one is 1, 1 minus 2. There's root 3, which I put somewhere. So the joint eigenvalues are 1, 1, minus 1, 1, and 0, minus 2. Okay. So the states are labeled by this and this in the three-dimensional representation. So I'll start with a quantum state, which is labeled by this superselection vector, for any one of them. So let me see what happens. What will I do with cascade?
What is the dynamics of that?
Which one?
What
Huh?
is the dynamics of the evolution on the?
That's what I'm going to do. That's what exactly I'm going to do. Okay. So I diagonalize it. H0 will not change it because it is gauge invariant. All gauge transformations are.
So this is the Hamiltonian underneath those things.
This is the chemical potential I have added. The chemical potential I mischievously choose to be some terms in the Hamiltonian, some terms which does not commute with cascade there. The test function here will not commute to the cascade there. By hand I choose. Okay, which I can do because you can choose anything you like. I choose this because I can do calculations. And I choose two terms. One is lambda 1, because the other one I choose lambda 3 for diagonalization. The other is lambda h. Then I will do. So this will change when I tell about it. H0 won't do anything to this system. It won't change the supersymmetry. But lambda 1 is lambda 3 don't commute. So it shall start changing. And lambda h. So you have to see how this operates, changes the supersymmetry operator. And I will choose that mu1 over mu8 to be irrational. As you remember. Let me do irrational things. And so there are two states which come in Q cascade.
That's how the area curves come. So it curves on polaris.
I know.
One angle and another angle.
Yes.
Then if they are irrational, the area will curve.
It's exactly the same situation. That's why I talked about it, but something new happens. Because you never return to the torus. I'll show you.
If it is irrational, it will not return.
No.
If it is rational, it will return.
No, that you are saying take a torus, even torus you have an orbit. Now, the cardinal torus is a torus. This one starts at some point in the cardinal torus, but it never returns to the cardinal. There is infinity of cardinal tori in a suit because it is conjugated, you get another torus. It can go. So this one jumps from torus to torus to torus and keeps going. So this is even more complicated. And how do I discuss with orbit? I don't know. The other case of the dynamic is there are many proofs that the orbit is dense. It's already in Turing's book. Here I don't know.
Everything's affected by constellation. So, something like see.
You can't do that. You cannot do because the superposition sector changes. Because I am changing the operator diagonalizing the two superposition sectors. Like the two transformations I am writing for Q cascade till then, the difference is not a Gauss law. The difference won't vanish. So it's not a Gauss law, it won't change. So it will actually change the expectation values of operators in the system. So the system, the situation here is much more complicated and very rich. So I actually wanted to find out what it is. So how it goes to show you. I exponentiate cascade for lambda 1 and lambda 3 as I told you. Lambda 1 and lambda 8 commute. So the exponentiation is simple. You get the same. Okay. So this is the operator which changes the chosen eigenvalues of lambda 3 and lambda 8. This is lambda 3 and lambda 8. And this one is changing. Is acting on a vector state with entries ABC with eigenvalues as I told you. And if it is all the time only hypercharge, so 0 minus 2, then this object will only change it by that will give 0. Lambda 1 is 0, 1, 1, 0. So that will give 0. This one will be diagonal, so it won't change. So that vector will not change. This is what I call color deconfined phase. But take any other state. What will happen? So, yeah, here 0, 0, 1, it will never change and it will change the phase. But the period is some I over mu h. Okay? So, after some period, it will go back. So, it will be some circular orbit. Okay. But if I take any of the other state, and this is irrational, you'll find that it never closes. Okay. So, that orbit, as I told you, has the structure of a recurring orbit, and the expectation value of any one observable will be 0 by averaging over time. Okay. It will not know where to sit. It will average to 0. Okay. Is it color confinement? I don't know. This is what happens in this model for quantum field theory, which I have written down. If you change the quantum field theory, I have written down, and something else may happen. So I think there are further arguments I can give, but this may not be completely off the hat. Okay. So let me finish off by asking an open question, which is related to what Balachandran was saying. The question is, if the color deconfined phases are attractors for the color confined phases, in the odd, vice versa, I don't know, because color confined phases are the ones which clearly are dense. There are huge number of them. Okay? They are given by irrational numbers on the real line. So there are a huge number of them. Okay? But these are isolated points where you fix, for example, mu1 over mu8 is rational, it will go back to the original torus after a finite number of times. Okay? So, so that situation is different. Okay? So, the irrational ones are dense, so you would expect that maybe the rational ones, the ones where there is deconfinement are fixed points. But how do I test it? I don't know, because this is a quantum theory. Classically, we know what to do, beta function calculation. You take the beta function and disturb it. You don't care about unitarity, you just disturb it and see what happens. You look at the frequencies of the quasi-normal modes which you are like. Here, that is not the case. If I do some perturbation, what it means is that I'm changing my unitary operator of evolution a little bit. But it is a unitary operator. So if I change it, it will simply start evolving wherever I change it again and never go. There won't be a relaxation of the original thing. So they think original thing is starting point. So I don't know how to analyze this issue. I also thought about this POPMs, some of you know, this positive operator value measures, whether I can do it that way also, and I don't know how to do it. Okay? So I would say that this is a very interesting question, which I don't know how to answer. So I'll stop here. But and I also told you that my friend Arshad is trying to simulate. There are more things that happen, which I have not. Here I am going on seeing how an abelian algebra is going to emerge, which I think is, for me at least, is a very interesting thing. And I found that Hagen also had a discussion about this. That is maybe giving a clue of observations. But I want to tell this paper and then I'll stop. A problem similar to this was discussed by these people long ago. And recently, Paolo Facchi has been discussing it. What is the problem? Very simple. You take a particle on a circle. Okay? But the domain of the so and you take the momentum operator as your Hamiltonian, I d theta. Very simple. Then the domain of the Hamiltonian are smooth functions which change by a phase as you go around. You can change by some phase. So I take psi of 5 and psi of 5 plus 2 pi can be some phase exponential I theta times psi of 5. Every one of these for a fixed phi defines a self-adjoint operator. But the spectrum depends on phi. And if you change phi, the spectrum changes. There is a spectral flow. Okay? You can study this. This is used for discussion of anomalies. There is a spectral flow. And furthermore, the domain changes to the Hamiltonian. So they have discussed what happens to time evolution in this case. Suppose I take this theta, which is the quasi-periodicity, make it a function of time. Suppose I make it a function of time and let it change in time. How will I multiply? So it is changing with time. So the domain of the operator x is changing with time. Can write it down. Then how will I multiply exponential IHT? So it is now exponential IH theta of t because it depends on the phase. But two different thetas. So I evolved it by some time. By that time, I evolved it from 0 to some t1. Domain has changed. So how do I evolve next time? And next time, and next time. So there is an issue of defining the total formula. If you know the total formula, there is an issue. How do I do it? Because the domain is going on changing. So the multiplication of the unitary operators is not well defined. You have to tell how am I going to fix the domains and put them together. And from what I read from the paper, Trotter already discussed it in his original paper. And they have revised it and showed that the multiplication of the unitaries involves some new product. So you have to label the Hamiltonians by this angle, and a new product appears in this Hamiltonians. They call say h theta 1 star is theta 2. And that plays a role in evolution as you keep changing the time. I have not fully understood the paper, but they also claim that because of this change, there's a fixed point in the evolution in their calculation. And for some fixed, simple cases, like they'll say zero, some interval, they find that the fixed point corresponds to the Dirichlet boundary conditions. So when you keep evolving in the Trotter formula, it evolves to the Dirichlet boundary conditions. That they claim they have proved it. I talked to Manolo, who is one of the authors, and he assures me that this is the case. I have not understood how, and I don't know how it applies to this work I have presented to you. I think this will be a very interesting problem, but yeah, so the time evolution itself may be drastically changed. So with that, I'll stop because I have exceeded my time by 15 minutes. So I'll stop. And now we can discuss the goal.